Hello. Hello everyone, my name is Filip Geppert and today we are going to play with OpenCV a little bit and then we are going to see how to effectively extract image features. We're at PyData Warsaw 2019, it's December 13th. Quick off topic, today it's Friday and many people protest against climate changes happening around us. I believe that time for action is now and we as data developers can deliver a significant message based on signals that planet Earth sends to us every day. But okay, today we are going to work on computer vision problems and somehow go-to solution is to throw neural net on it and wait what happens. Today we are going to use slightly different method and we will use OpenCV to extract features. I prepared two projects for this talk. First one is a project where we will detect street lanes, and the second one, in the second project, we will build a script that will decide whether there is a car in front of us or not. So what you will learn today, you will see what are image color spaces and how you can convert them, what's image filtering, especially in the context of color filtering, what are image arithmetics, so how you can add, subtract images, how you can reduce noise in your new data set, which is image, what is edge detection, how you can detect edges, and based on edges, how you can calculate lines, what's motion detection, especially in the context of the video and consecutive frames coming in sequence. And at the end, we'll see how we can create the famous bounding boxes that you probably see in every computer vision visualization. Starting from the first project, street lane detection, the path is the following. First, we will detect left lane, which is yellow. Secondly, we will detect right lane, which is white. Then we will reduce image noise, then detect edges, and finally, we'll create a logic to decide if something is street lane or not. Okay, so you read an image, and image is basically a three-dimensional NumPy array, and probably you're most familiar with the BGR or RGB color space. The shortcut stands for red, green, blue, and you can think of it as a three-dimensional color space where 0, 0 point is black color, and 255, 255, 255 is white color. So any combination, any color that you can think of always lays between these 2 points. And with this approach, this is not a very intuitive approach, and there sometimes comes problems. Imagine that you would like to filter the whole yellow color space. Probably you will start from light yellow, which is 255, 255, 0. Then you will move to the darker color, 204, 204, 0. So one can come up with a logic that yellow starts at 204 and ends at 255. But actually, if we apply this, we get something that is completely not yellow. So HSV color space comes to the rescue. It's more human intuitive, and it has 3 channels that are responsible for completely, maybe not completely, but very different things. First channel is a hue channel where we have the whole color palette. And it starts at 0, ends at 179. So any color you can think of, you can always be sure that if you select the appropriate range, will be there. Second channel is a saturation, which tells us how faded our color is. So 0, it's completely faded. 255, it's not faded at all. And by the way, this is you can think of it as a percentage scale. And the third channel is a brightness channel, which tells us how much black color our color has. So let's start coding. Let's read our image in OpenCV, and as you can see, there are one-liners thanks to which we can read an image, and then we can convert our color from the RGB color space, which is a default one, to the HSV color space. Then we define our lower and upper range for the yellow color by specifying the list with 3 integers, and then we use the in-range OpenCV function where we give input image our lower and upper boundary, and you can see the result here. If you go to the right lane, which is a white one, you basically see the output of the same operation. And this is usually what you will have once you start working on your first image processing project. Apart from the section of the image that is interesting to you, you will have a lot of noise. I mean, every data set has a lot of noise, but luckily there are many methods to overcome this obstacle. So I wanted to firstly introduce erosion. What erosion is, in its basic form, it has 3 parameters: input image, the image from the previous slide, the kernel, which is a square that we slide from the left to the right, from the top to the bottom. We specify the size of this kernel, and what erosion does, it diminishes the effects of white pixels that lay on the boundaries of our shape. So basically, it slides the kernel. If all pixels are white in the kernel, it sets the center value as a white pixel. If there is at least 1 black pixel in our kernel, then the return value will be black. The opposite operation is dilation, when we also slide the kernel through it, and this time the kernel checks if all pixels within the kernel are black. If all are black, the result is a black pixel. If there is at least 1 white pixel, the result will be the white color. And the iteration parameter, tells you how many times this operation should be done. The method for reducing false positives from your data set is opening. So this is erosion followed by dilation. So it will quickly let you reduce the effect of white pixels that you can see on the left. And the opposite operation when we reduce false negatives is closing. So it reduces the pixels that are black within our object. So coming back to our project, we apply erosion on our image. So hopefully you remember that we had some red pixels on the top part of the image. So we managed to reduce majority of these. As always, if you increase the number of iteration in this erosion procedure, probably at the very end you will have completely black image. So once we have our left lane candidate, right lane candidate, we want to combine this into one image. So use OpenCV add function. And a quick note here, we used addition in OpenCV. It's because it's saturated addition. So as you remember from the beginning, I told you that we usually start on the 0 value in color space and we end on 255. So that's exactly what saturated addition does. If we add 240 and 20, the result will be 255, as there is a floor in the ceiling in our image values. So once we have our combined results, we would like to detect edges, and we use the canny edge detection in its basic form. So we provide 3 values: our input image, the threshold 1, and threshold 2. How canny edge detection works? Firstly, it applies Gaussian filter. It's another filter that helps us to reduce noise. Then the pixel gradient strength and direction are calculated. What's pixel gradient? You can think of it as a rapid change from the white to black color. This is going to be very high gradient. White to white-ish color is not high gradient. Then we normalize edge candidates. So if you imagine the image, the edge is always a transition period, but we are interested in very sharp edges. So there are always gradient candidates for deciding if something is an edge or not. So basically, from the candidates, we choose the maximum value, and then we apply the thresholding parameters. So if the value of the gradient is above the second threshold, the pixel is going to be considered an edge. If value is between first and second threshold, it depends whether algorithm previously classified the neighboring pixels as edges or not. And in a last case, if the gradient is below the threshold, the value of the pixel is not going to be considered an edge. So this is the result of our edge detection. Clearly, we can see the left and right lane are detected. And based on that, these are still pixels, so we don't have any understanding whether there are lines in our image or not. So we are going to use hue probabilistic function. It's probabilistic function because it only considers the subset of your data set from the points that you've seen on the previous slide. It has a lot of parameters, I know, but stay with me. Okay, so firstly, we need to define what the line is. You, of course, know the line equation in Cartesian coordinates, but also we can represent line in polar coordinates, where we have two crucial parameters, which is rho, which is the distance from the coordinate system, and theta, which is an angle with horizontal axis. So what hue probabilistic function does, it's basically, let's imagine that white points are our edges. So it loops over all possible lines in our image, and we specify the loop step by specifying rho and theta parameter in our function, and it starts classifying the lines and calculates how many points overlay with our line. So for the first line, we have 0 points that coincide. If you consider the second line, we have 1 point that coincides. And for the last line, we have 3 points that coincides. So basically, this is how you get intuition what the line is, and this is why you use threshold parameter. By specifying threshold, if we specified threshold parameter equal to 3, then the last line would be considered as a line, and the previous two wouldn't be considered lines. The last two parameters, minimum line length, specify what's the minimum length of the line in pixels for the line to be considered as one, and the max line gap prevents us from lines being occluded. So imagine that if we have a line here, you take a picture somewhere there, and then for the short part in image, the line is not visible, then it continues. So this is exactly why we have this max line gap parameter to prevent us from the occurrences like this. So we detected lines in our image, and this is the perfect moment to invite you to write logic about determining if something is a straight line or not. So I invite you to visit my repository. I uploaded the whole code before my presentation, so you can see what's the logic for determining if something is a straight line or not. So in that method, it's basic Python, and we check whether the line has a straight line characteristics such as length, direction with the horizontal axis, or the width. And once we apply everything, once we combine all the procedures, we have our results. So as we can see, the left and right line are detected quite good. Second project, second exercise for the stock, the motion detector. So the procedure is the following. From now on, you should think of any video as a sequence of images that we can analyze in loop. So for our project, we are going to take a first frame of the video where we know that there is nothing in front of us, and we are going to consider it as a template. For every next frame, we will compare and calculate the pixel difference, and then we're also going to consider only area limited by straight lines that we calculated in the previous exercise. And for the large group of pixels that change for the large intensities, we are going to assume that this is a car that is likely moving in front of us. So we start from reading our image, but then we know that for this exercise, we don't have to calculate it in a three-dimensional space, so we convert it to grayscale color space. The advantage of converting image to the grayscale is, of course, that we have less data to analyze, so everything computes faster, but we also lose some important information that, for example, we were able to use in the previous exercise. Then we apply blurring. What's blurring? Our images come in sequence, and for example, there is a lot of noise that comes here and there. The buildings on the left side can change, the whole environment can change, and what blurring does, it basically normalizes the images that come in sequence. How blurring does, we specify the kernel size, and within that kernel, we sum all the pixels, and we calculate the mean value, and we set it as a center value for the pixel. Then we calculate absolute difference. We subtract our current frame from the template that we set at the beginning of the video, and then we mask and the result of that operation is presented on the left. What's the center image? It's our mask. So this is our region of interest. We want to only consider changes in that area. And we use bitwise AND in OpenCV handy method to basically tell, OK, I only want to use the area from the left image that is highlighted in the center image. So the result, you can see the result on the right side. So once again, grayscale image, values from 0 to 251. And this is when we know that, for example, for these pedestrian lanes, we don't want to consider this as a change. We only want to consider if there is a rapid change in our image. So this is when we use the threshold function. In the threshold function, we apply the threshold value. So we say if the pixel is below the threshold value, is going to be equal to 0. If it's higher than threshold value, is going to be equal to max value. And we specify this type of thresholding by saying, OK, we want to have binary threshold. So in our output image, we are only going to have 2 values of pixels possible. Then, as we can see on the left, we have 3 white areas visible. So the next part is going to be finding contours. What are contours? As name says, is basically the line that frames the area. So we calculate contours, and in the find contours method, we specify what kind of contour we are interested in. So in our case, we are interested in external contours. And we are also going to tell to OpenCV, OK, we want to, as a return value, we want to have very specific, very precise representation of our contour. You can also tell that you want to simplify this, and for example, as a result, only get a rectangle, 4 values of points that are going to frame your contour. And then we get our contours, and for these contours, we calculate the area, the pixel area of the contour. The next step, we filtered, so we set a threshold. If the rapid change was above a certain threshold, this is likely a car, and for that, we finally draw a rectangle. And in OpenCV, you draw a rectangle by specifying what's the top left corner of the rectangle and bottom right corner. You can also specify its color and thickness, of course. So this is the result. We detected car in front of us, and we are also able to detect that car disappears. So basically, there is a clear road in front of us. But beware, because light has changed, so we cannot move further. So, as a summary, we've done a lot today. Sometimes this is the whole Udemy course, so hopefully you're satisfied. First, we've seen what are the color spaces, what's BGR color space, what HSV color space, and how you can quickly convert these, and why you can sometimes consider using one color space in place of a default one. Then we've seen what's image masking, and also we've seen what's image filtering based on color values. We also have seen how you can add and subtract images, white saturated operation. Then we've seen what are the 4 methods in OpenCV that can help you reduce noise coming in your image. So we defined erosion, we defined dilation, opening and closing. Then we've searched for edges in our image, and based on edges, we calculated lines that are there. Then we analyzed the video in the context of motion detection and the comparison of the values that change rapidly. Finally, we've seen image thresholding methods, and we also have seen how you can create bounding boxes. My subjective tips for you: hopefully you will start your first project in OpenCV. So display every result. This is way of debugging OpenCV code, and in my opinion, this is the ideal way of checking whether the operation that you applied is appropriate and worked properly. Second, play with method parameters, understand parameters, don't go with default ones. Really, sometimes by changing, for example, in the probabilistic function, by changing the step size, you can speed up computation time significantly, which, for example, matters when you run some operation in someone's browser. And finally, simple is better than complex. So before going with neural nets, start with something simple that you can do in OpenCV in a few lines or slightly more than few. Check the results, validate your results, and if this doesn't work, of course, go with something more complicated. What's next? There are really great tutorials provided by OpenCV community. So I invite you to check their documentation, see their tutorials. Of course, the whole source code, input images, video, and the whole talk is already uploaded to my GitHub repository. So I invite you to go there, download, and finally, the best way to learn something is by starting your first project. So go ahead and create your first computer vision system. From time to time, I write blog posts regarding data science, machine learning, computer vision, data engineering. So if you want to read some free tutorials, I invite you to go to my blog and sign up to my newsletters so that you are always up to date with what's new there. And as always, stay in contact on Twitter and let's talk to each other. Thank you very much.
Thank you for your presentation.